In the last class, we have gone through formation of digital image, and we have seen two important concepts related to formation of digital image, and these concepts are sampling and quantization. So after sampling and quantization, we come up with a digital image. So the result of sampling and quantization is actually a matrix of real numbers. So we have seen this representation of image earlier. So any digital image, right? So this is the digital image. This is a grayscale image having only the gray shades, right? So this image is being represented with a matrix. So here you look at this matrix A, and this matrix is of size m by n. This m is nothing but the number of rows or height of the image. So in this particular case, m is 256. So number of rows or height of the image is 256. So we are having number of rows equal to 256 in this particular matrix, right? So here m is 256. So height of the image is 256 and width of the image is also 256. So n is also 256. So this image is represented by a matrix of size 256 by 256, right? So here is the matrix A, wherein we are having individual elements, m rows and n columns, right? So this individual value is representing one small unit in this image. So this individual value in the matrix is actually representing a small individual discernible detail in the image, and that is known as a picture element or a pixel or a pel. So each pixel is being represented with some value, some number, and that is being stored in the array, right? To make it more simple, what we have done is we have divided this 256 by 256 image into 8 by 8 blocks, right? And this particular small block of size 8 by 8 is being depicted here with the values, right? So these 8 by 8 block is having 8 rows and 8 columns, right? So each individual element in this particular matrix is depicting the value, and this value corresponds to the gray shade in that particular image or that particular block, right? So we have seen this in the last class. Now let us proceed how actually, or why we are saying that we are having the number of intensity values equal to 256, right? So if we are digitizing the image, we require the decisions about three different quantities, m, n and l, right? So what is m and n? That is the size. M and n denote the size of image, right? Size of the image is being denoted by m and n. So m is the height, n is the width. So number of rows and number of columns in the image, right? So whenever we are digitizing, we need to take the decision about three values. What is the size of the image? Okay, and that is denoted with these two values m and n, and we also need to consider the number of gray levels L, right? The number of gray levels L. So here, size of the image or m and n are the positive integers. M and n are the positive integers. So we may have the size of the image 100 by 100. So positive integers m by n. So number of rows are 100, number of columns are 100. I may say that I am having the image of the size say 300 by 472. So what it means? It means that in my image I am having 300 rows and 472 columns. Or in other words, height of my image is 300 and width of my image is 472. Right? So this is how we are mentioning the size of the image. So m and n are positive integers. And one more value we need to decide, and that is L. So L denotes the number of gray levels. And typically the number of gray levels are denoted L equal to 2 to the power k. 2 to the power k. So what is this k? K is actually the number of bits those are used to store individual value or individual pixel, right? So this k represents the number of bits those are being used to store individual pixel or individual value in our image. So 2 to the power k actually is giving us the number of gray levels in our image. Right now we are talking about only gray level images. We are not talking about color images, right? So number of gray levels are given by L equal to 2 to the power k, where k is the number of bits. Those are being used to store one pixel or one value. Right? So if I'm having the image with size m by n, if I'm having the image with size m by n, right? And if k bits are being used to store individual value, individual pixel, then the total number of bits required to store my digitized image is given as b equal to m into n into k. Are you getting me? Yes? Please speak up.
Yes, ma'am.
Right. So, what is k here? K denotes the number of bits. Those are being used to store individual value, individual pixel. So if I am having the image of size m by n, and if every pixel is being stored with k bits, then the total number of bits required to store my digitized image is equal to m by n by k. If I am having the square image, if I am having the square image, that means if the number of rows are n and the number of columns also equal to n, right? Then the square image with the dimensions n by n will require number of bits equal to n square k, where k is the number of bits required to store individual pixel. I hope the concept is clear. Shall I proceed?
Yes, ma'am.
Yes,
Right.
ma'am.
Now, let us proceed with some examples. So here in this table, the number of storage bits are being computed for various values of n and k. So we are considering the square images of size n by n. Okay, and as we go on changing the number of bits required to store 1 pixel, the size of my image or the number of bits required to store the image obviously go on changing. So see here, if I am having the value of n equal to 32, right? So I am having the image of size 32 by 32, 32 rows and 32 columns. So number of pixels, number of total pixels, I will be having 32 by 32, 32 into 32. Right? Now, if each pixel is represented, each pixel is being stored using only 1 bit. If each pixel is stored using 1 bit, then the storage requirement would be 32 by 32 into 1. So 1024 bits will be required to store the image of size 32 by 32, and each pixel is stored using 1 bit. Okay. Now, if I am having only 1 bit used to represent 1 pixel, then the number of gray levels I'll be having in my image, how many gray levels? Gray levels L is equal to 2 to the power k. Here value of k is 1. So 2 to the power 1 means the number of levels, gray levels I'll be having 2. Right? So this is a binary image wherein I'll be having only 2 intensity values, 0 and 1. Getting me? Only 2 intensity values, right? 0 denoting black and maybe 255 denoting white. So only 2 intensity values I'll be having. Okay. Now, if I'm having the same image size, say 32 by 32, right? But each pixel is being stored using 2 bits. So value of k is 2. So L equal to 2 to the power 2, meaning I'll be having 4 gray level values, 4 gray scales, right? And the size of my image in number of bits would be equal to 32 into 32 into k, that means 2. So 32 into 32 into 2. So it is the size of my image in bits would be 2048. Is that okay? Yes?
Yes, ma'am.
Right. Now, see here, this is the table that is being prepared using different values of n and different values of k. So, as I go on increasing the value of k, right, beginning from 1, 2, 3 and so on up to 8. So, if I am representing 1 pixel using 8 bits, then I'll be having the number of gray level values equal to 2 to the power 8. That means 256. So number of levels L equal to 256. Whenever individual pixel is being represented with 8 bits. So if size of the image is 32 by 32 and individual pixel is being represented with 8 bits, then size or the number of bits required to store that 32 by 32 image would be 8192. And the number of gray levels would be 256. Are you getting me?
Yes, ma'am.
Yes.
Yes, ma'am.
Right. Now, the image that we have seen earlier, the cameraman image, right? That is the most popular image you may find in many of the digital image processing books, right? that image is of size 256 by 256. Right? So we are having number of rows equal to 256, height and width also is 256. Right? And it is a grayscale image wherein every pixel is represented with 8 bits. So I'll be having 256 grayscale levels, right? And the size to store 256 by 256 image in my disk would be, number of bits required would be 424288. Right? So this is 256 by 256 multiplied by 8. Is that okay? Yes?
Yes, ma'am.
Right. So this is how actually the digital images are being represented, and if we store those digital images in memory, then this is the statistics, how many bits are actually required to store the digital image in terms of the size of the image and the number of bits used to represent or to store individual pixel. Okay, so let us proceed now with one important term, and that is resolution. You might have heard this term many times, resolution. Have you heard of this term, resolution?
Yes, ma'am.
Yes. So whenever we talk about any image, right, we decide the quality of the image based on resolution. Do you agree with me?
Yes, ma'am.
Right. So let us see now what actually the resolution is for the digital image. Okay. Now, whenever we talk about spatial resolution, or rather whenever we talk about resolution, we are having two kinds of resolutions. We are having spatial resolution and we are having intensity resolution, or we are having grayscale resolution. Spatial resolution and intensity or grayscale resolution. So we are going to focus upon these two terms now. Okay, so let us first talk about spatial resolution. So actually the process of sampling that we discussed in the last class, the process of sampling determines the spatial resolution of an image. I'll repeat. The process of sampling determines the spatial resolution of an image. Right? So what it is actually, it is the measure of smallest discernible detail in the image. It is the measure of smallest discernible detail in the image. Right? And this spatial resolution measures the measures of spatial resolution must be stated with respect to some spatial units. So what I mean by that? Let us consider few examples, right, of image resolution, right? So many times, whenever you must have heard about, whenever we print something, right? How actually the resolution is being determined? The resolution is being determined in terms of DPI. What is DPI? Yes? Anybody who knows the full form of DPI? Whenever we go for printing something, right, it asks for one quantity, whether it is uh, 300 DPI, whether it is 200 DPI.
Is that DPI means display per inch, ma'am? Display unit per inch.
It is dots per inch.
Yes.
Dots per inch. Right? So many times you might have seen whenever you scan a document, right? You need to set one parameter. And what is that parameter? Whenever you are scanning something or whenever you are giving the command for printing something, you need to pick some value for dots per inch. So typically we print in 300 DPI, 200 DPI, 600 DPI, or even 2400 DPI and so on. Correct? So what it is? Dots per inch. Right? So dots per unit distance is really very important. Dots per unit distance. So typically this is DPI is the measure that is being used in US, and we are also following the same unit, dots per inch. Right? So to give you an idea of quality, right, the newspapers are printed with a resolution of 75 dots per inch, newspapers. Right? So what is the quality of printing for newspapers? Typically, the resolution is 75 dots per inch. Right? If we go for magazines, average quality magazines, then the resolution of printing the magazines is typically 133 dots per inch. Right? If we go with some kinds of glossy brochures wherein some art paper is being used, right, and some images are being printed, then such kinds of glossy. Please, I would request all of you to be on mute. So if we go for some glossy brochures, then these are having the resolution maybe typically 175 dots per inch. Right? If we are looking at some very good quality book, right, then maybe the quality of printing would be 2400 dots per inch. Right? So which is better quality, 75 or 2400? Yes, whether 75 DPI is good or 2400 DPI is good.
2400.
2400 DPI is a good quality. And what is the reason?
More dots are filled in the same area, so there is more detailing.
Yes, correct. So to be meaningful, measures of spatial resolution must be stated with respect to some spatial unit. Here the spatial unit that we are using is inch, right? So per unit inch, how many dots or how many pixels are being depicted? That is what we are saying. So if more number of pixels we have, obviously more number of details, it is possible for us to print or to visualize more number of lots of details. Right? So image size by itself does not tell everything about that image. Right? For example, if I say that my image is say of size 1024 by 1024. Is this meaningful statement? I'm having the please be on mute. Unless you are given a chance to speak or unless you are having any doubt, be on mute. Then only you can unmute yourself and ask the doubt or answer the question. Don't disturb others. So if I'm saying that my image size is 1024 by 1024. So is it a meaningful statement to understand what is the quality of my image? Yes? Please
No,
speak
madam.
up.
No.
Then what additionally I need to specify?
Madam, we can add some unit for that, like pixels, how many pixels it has.
So 1024 by 1024. These many pixels I am having. Image is having the resolution of 1024 by 1024. What it means? It means I am having 1024 pixels, see, in a row, and I am having height of my image also 1024. So 1024 by 1024 image I am having, meaning I am having 1024 rows and 1024 columns. So whether it is enough, whether it is a meaningful statement to understand the quality of my image?
DPI should also be mentioned.
Yes?
DPI should also be mentioned.
No, that is not the case. DPI is typically used in printing industry, dots per inch. Right? Dots per inch. Here, whenever I'm saying, I'm visualizing one image, let us assume, right? And or I'm saying that the image size is 1024 by 1024. It is not enough unless I mention the spatial dimension that is occupied by that image. Right? When size by itself would be meaningful, size itself, size of the image itself would be meaningful if I'm having the comparison between the imaging capabilities. For example, if I'm using a digital camera having the resolution 20 megapixels, right? And if I'm having another digital camera having the resolution 8 megapixels. So I'm having one camera with resolution 20 megapixels and I'm having another CCD camera with the resolution of 8 megapixels. Now assuming that both the cameras are equipped with some comparable lenses, right? And assuming that the comparison between the images is taken at the same distance, then I may say that 20 megapixel image is far better than 8 megapixel image. Because the number of pixels those are being used to represent the image are more in 20 megapixel camera than 8 megapixel camera. Right? The number of pixels are more in 20 megapixel camera. Right? But I'm having here one assumption, and that assumption is both the cameras are equipped with some comparable lens. So to determine the quality of the image, lens of the camera will also contribute. Right? To determine the quality of the image, the distance from which the picture is being taken, it can also matter, right? So if I'm comparing two images, those are being acquired, one with 8 megapixel camera, another with 20 megapixel camera, then I'm assuming that the image is being acquired from the same distance, right? And the lens that is being used in both the cameras is comparable. Then I may say that 20 megapixel picture is far better than 8 megapixel picture. Or 20 megapixel is high resolution compared to 8 megapixel because I'm getting more details. Right? I hope you must have understood the concept. So spatial resolution actually deals with the number of small elements. Those can be measured in some specific, given some specific spatial units. Right? So spatial resolution must be stated with respect to some spatial units. Right? So I hope now the idea is clear. So whenever we are using this concept of sampling, what we do, given such kind of image, right, instead of considering the detail, instead of considering each value, right, at each coordinate x, y, what we do, we sample x-axis and we sample y-axis with some uniform intervals. What it means, instead of picking up each x value and instead of picking up each y value, what we do, we sample that image with some sampling interval. So we may say that we may come up with alternate x values, right? Or we may say that we will be having one sample after 4 samples. Likewise, similarly on y-axis also we go on sampling. So instead of considering each pixel, we will be considering few of the pixels after sampling, and whichever are the number of pixels, those are sampled on x-axis, and the number of pixels, those are sampled from y-axis, those actually determine my size of image. Okay, so given original raw image, what I'll do, I'll sample x coordinate also and I'll sample y coordinate also. So whenever I'm saying that I'm having the image of size 256 by 256 after sampling, right, I have picked up 256 x coordinates and 256 y coordinates, and at the intersection of that x and y coordinate, whatever is the value, only those values I have picked up to come up with the image of size 256 by 256. Right? So this determines the spatial resolution of the image. I hope the idea is clear now. Yes?
Yes, ma'am.
Fine. Now the next concept is intensity or gray level resolution. Intensity or gray level resolution. So it is smallest discernible change in intensity or the gray level. It is smallest discernible change in intensity or the gray level. So typically, due to some hardware considerations, the number of gray levels is usually an integer power of 2. Integer power of 2. Number of gray levels are typically integer power of 2. Right? So if I am using number of bits, 1 bit to represent 1 pixel, then the number of gray levels L equal to 2 to the power 1. That means 2. If I am using 2 bits to represent 1 pixel, then the number of intensity values, those I'll be having equal to 4. Right? So if I'm having the image whose intensity is quantized into 256 levels, then it is having 8 bits of intensity resolution. 8 bits of intensity resolution. This means that each pixel is being represented using 8 bits. Is that okay? Yes?
Yes, ma'am.
Right. Now, go through few examples. So look at this picture on the screen. So what we have? We are having this original image of size 1024 by 1024. Right? So I'll be having the height of the image equal to 1024 and width of the image is also 1024. So this is my spatial resolution for this particular image. Is that okay? And the number of gray levels, those are being used to depict the details of the image are 8 gray levels. Or the number of gray levels are 256 gray levels. 256 gray levels. Right? So this image is having the spatial resolution 1024 by 1024. Right? And this image or every pixel of this image is represented using 8 bits, and that is why this image is having 256 gray shades or gray levels or intensity values. Right? Now this is my original image. If I am subsampling this image, right, so that I can have the size of the image as 512 by 512. So what I can do to subsample this particular image? I may subsample this image by omitting alternate row and alternate column of the original image. Is that okay? So what I'm trying to do? I'm trying to omit alternate row and alternate column from the original image, and I'll be having this subsampled image of size 512 by 512. Right? The number of gray levels still 256. Okay? Now, once again, I'm subsampling this image so that the spatial resolution now for this image is 256 by 256. Still, the number of gray levels used are 256. So, this is how I go on subsampling the image till I reach to the final image size, that is 32 by 32. And still, the number of gray levels I am using are 256. Is that okay? So, this is high resolution image having 1024 by 1024 pixels, right? So what I'm trying to do, I'm sampling this image, I'm subsampling this image so that alternate x coordinate and alternate y coordinate I'm picking up. So I'm reducing the resolution, right, to half. So I'll be having 512 by 512 image and so on. Right? So I'm subsampling. So I'm sampling alternate x value and alternate y value. And I'm getting the image resolution that is half of the earlier one. Right? Now, let us look at this picture now. So what we have done here, just look at this picture. What we have done here, we are having the original image, that is 1024 by 1024, 8-bit image. Then this is 512 and 512 image, right? But this image is resampled such that the size of the image once again is 1024 by 1024, right? So this is original 1024 by 1024 image, and this is depicted using the same size 1024 by 1024. What about this? This is the second image that we had. So this image 512 by 512. So what we did, this 512 by 512 image is resampled, right? And once again, the image size is 1024 by 1024. Okay. Now what about this? This is actually 256 by 256 image from our previous slide, and that is resampled to get 1024 by 1024 image, and so on. So what about this? This is originally the 32 by 32 image that we had in the previous slide, and this image is resampled to come up with the size of the image as 1024 by 1024. Yes, very true. So as we go on reducing the resolution, spatial resolution, right, the quality of the image is also degraded. So see here, if we try to look at this 32 by 32 image, right, which is actually zoomed, you may say that it is zoomed, right, so that it will fit into the size of 1024 by 1024, then the quality, the pixels are being blurred, right? So as we go on decreasing the spatial resolution, the quality of the image also degrades because we are losing some information from the original one, right? So I hope now you must have understood the concept. Now let us see one example of image resolution, which is intensity resolution or grayscale resolution, right? Now see here the image. So we are having this original image of a skull, and that image is of size 452 by 374. Okay, and this is having 256 gray values. Is that okay? This is my original image of size 452 by 374, right? And this image is having 256 intensity values, right? Now, what I'm trying to do is I'm trying to manipulate the resolution of the image with respect to intensity value or with respect to grayscale value, right? Keeping the size of the image, keeping spatial resolution same. So I'm keeping spatial resolution constant or same. So if you look at each image is of size 452 by 374. So I'm not sampling on x-axis or on y-axis, right? I'll be having the entire image, all the coordinates as it is, 452 by 374. But what I'm trying to do is, I'm trying to reduce the number of intensity levels, right? So if you look at this particular image, then this image is having the intensity values 128. So here I am having 256 intensity values. Here I am having 128 intensity values. Right? Here I am having 64 intensity values. And here I am having 32 grayscale values. So how I am doing this? By using the concept of quantization that we have studied in the last class, quantization. What we mean by quantization? Yes? Quantization meaning? Yes, please speak up. We have defined it earlier. Quantization meaning digitizing amplitude values. Right? What it means? In the last class we have seen, if I am having say intensity value 0 and let us assume that this is intensity value 255. So total number of intensity values I am having are 256. Now if I want to sample the amplitude values, or if I would like to quantize the amplitude values, what I'll do? Instead of using each intensity value, what I'll do? I will range. I'll be having some ranges of intensity values, right? So if I do it like this, 0 intensity and 1 intensity is one range. Then 2 and 3 is another range, and so on. So what will happen? I'll be having 2 intensity values in one particular range. Okay, so 256 values will be fitting in 128 ranges, because in each range I am having 2 values, isn't it? So if I do this, then if in original image, if I am having the intensity value 0 and 1, I'll be having some value for that, say 0. If I am having intensity value of the pixel in this range 2 or 3, then I'll use 2. Okay, or I'll use some mapping function for that. Okay, so 256 values will be converted into only 128 values, right? And if I would like to have only 128 intensity values, then each pixel need not be represented with 8 bits. It is possible to represent each pixel in 7 bits. So 2 to the power 7 is 128. Right? So it may happen that I am representing individual pixel in my image using only 7 bits, giving me 128 intensity values. Right? Here what I am trying to do, instead of representing each pixel, right, using 8 bits, still I am reducing it. So only 6 bits are being used to represent individual pixel. So the number of intensity values I am using here are 64. Here the number of intensity values I am using only 32. So original 256 values are being converted into 32 values only. Right? Similarly, if I go on, then this is the image having the intensity values 16. This is the image having intensity values 8. This is the image having intensity values 4. And this is the image having intensity values 2. So if you look at this image with intensity values 2, this is a binary image having only 2 shades of gray, white and black. So what we have done, we are keeping the number of samples on X and Y axis same, and we are going to reduce the number of gray levels from 256 to 2 in integer powers of 2, right? So 256, 128, 64, 32, 16, 8, 4 and 2. Right? So we are reducing the image resolution in terms of intensity. Is that okay? So see here, look at this. If you go on reducing the number of intensity values, you may see such kind of effect. Right? So there is no smooth transition between the grayscale values. There is no smooth transition. So you are visualizing here some kind of aliasing effect. See here, number of intensity values 8, right? So there is no smooth transition between the gray level value, right? Because a large range of gray level values are being mapped to same output value. Yes, so once again, if we go on reducing the intensity resolution, once again, we are losing the details and we may visualize such kinds of aliasing effects in our image. So I hope the concept of image resolution is clear. Image resolution in terms of spatial resolution and intensity or grayscale resolution.